So today we're going to be talking about alternating series. And an alternating series is a series where terms are alternately positive and negative. An example of an alternating series would be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus etc. And this can be written as a series from 1 to infinity of -1 to the n minus 1 times 1 over n. You know that this is an alternating series because, as you can see, each time the sign switches. With alternating series comes the alternating series test. And the goal of the alternating series test is to determine if an alternating series converges. So you have an alternating series from 1 to infinity of -1 to the n minus 1 times b sub n. This can be written out as b sub 1 minus b sub 2 plus b sub 3 minus etc. for all b's sub n greater than 0. Now, to determine if this alternating series converges, you have to satisfy two conditions. The first condition is if b sub n plus 1 is less than or equal to b sub n for all n. Now, what this means is basically is the series decreasing. And if that condition holds, then you move on to the second one. Is the limit as n approaches infinity of b sub n equal to 0? And if both of these conditions are satisfied, then you know that the alternating series converges. But, warning, the alternating series test only works for an alternating series. If your series is not alternating, then you must use a different method. Otherwise, you may come up with the wrong answer. Now that we know what the alternating series test is, we can move on to examples. A fairly simple example would be the series from 1 to infinity of -1 to the n times 1 over n. And up here I have written out my conditions just for reference. And now we know that 1 over n would be our b sub n. So now we take it to the conditions. First, is 1 over n plus 1, which would be our b sub n plus 1, less than or equal to 1 over n for all n? Now you can see that this denominator will always be greater than this denominator, since this is n and this is n plus 1. Therefore, because they're fractions, you know that the fraction with the greater denominator will always be less than the fraction with the n denominator. So this does satisfy the first condition, and it is decreasing. Now for the second condition, is the limit as n approaches infinity of 1 over n equal to 0? Well, we know that the limit as n approaches infinity of 1 over n is equal to 1 over infinity. We also know that 1 over infinity gives you a very, very small number, which is close to 0. So, the limit of n as n approaches infinity of 1 over n would equal 0, and the second condition is satisfied. Therefore, you know that this alternating series does in fact converge. For our second example, we're going to look at a series that's a little bit more difficult. So we have this series from 1 to infinity for -1 to the n plus 1 over the square root of n squared plus 2n minus 1. Right now there's no clear b sub n, so we're going to make it look a little bit nicer by taking the -1 n plus 1 and multiplying it by 1 over n squared plus 2n minus 1. This is the same thing, but now, clearly, this is our b sub n. Now for the conditions. First, is it decreasing? This series really isn't as clear-cut as the first series we did, so I'm going to plug values into our b sub n and determine whether or not it decreases. So if our b sub n is 1 over n square root of n squared plus 2n minus 1. Now, if we plug in 1, we get 1 over 1 squared is 1, plus 2 is 3, minus 1 is 2. The square root of 2, sorry. Now we plug in 2. 1 over 2 squared is 4, plus 2 times 2 is 4, so that equals 8, minus 1 is square root of 7. Plug in 3. We get 1 over the square root of 3 squared is 9, plus 6 is 15, minus 1 is 14. And we can continue. But we clearly see that the denominator each time is increasing, therefore the fraction is decreasing, and b sub n is decreasing. So the first condition is satisfied. Now, to determine if the limit as n approaches infinity of 1 over the square root of n squared plus 2n minus 1 equals 0. Well, we can tell that if we plug in infinity to the n's, we will get a very large number in the denominator. And as we said before, 1 over infinity gets very close to 0. Therefore, we can say that the limit as n approaches infinity of 1 over the square root of n squared plus 2n minus 1 does equal 0, and the second condition is satisfied. Both conditions are satisfied. Now we can say that this alternating series of 1 to infinity for negative 1 to the n plus 1 over n squared plus 2n minus 1 does converge. For the final example, we have a series of 1 to infinity for negative 1 to the n times 6n minus 1 over 5n plus 1. So we know our b sub n, which is 6n minus 1 over 5n plus 1. For the conditions, once again, I'm going to plug values into b sub n to determine if this series is decreasing. So for 1, we have 6 times 1 minus 1 is 5 over 5 times 1 plus 1 is 6. For 2, we have 12 minus 1 is 11 over 10 plus 1 is 11. For 3, we have 17 over 16. And for 4, we have 23 over 21. Now that you're looking at these fractions, you can tell that they are increasing, not decreasing. Therefore, the first condition is not satisfied, and you can stop there, and you know that this alternating series from 1 to infinity diverges. I hope you found this video helpful. Thank you for watching.